Okay, good evening everybody. I think I'm going to make a start now for tonight's revision hangout. We're going to look at additional science, chemistry, and we're going to do the second part to the additional science, which we didn't have time to do in the previous session. Hopefully you can all hear me as we're going through, and if you are inclined to write some comments, please just post them and I'll do my very best to answer as we go through. Again, as before, we'll go over the main content for the exams, and I'll give you some opportunities to have a look through some previous questions, which I'll then try and answer and show you how the marks are awarded. Again, this video is going out live, but it will also be stored on our page. So if you want to join us at a later time, or you want to pause it to take some more time for yourself over the question and then just resume, it's very able to do that. So I very much hope you find it useful, and I think now's probably the time that we'll get started. So in the previous session, we looked at the following topics for the additional science. We covered atoms in terms of atomic structure, ionic, covalent bonding, and metallic. And we looked at new materials, alloys and polymers. We looked at the vast majority of chemical calculations. We didn't look at percentage yield, and if I've got time, I'll quickly try and go over that again tonight. And then finally, we looked at the data sheets, specifically the information they hold and how they can be used. For tonight, we're going to look at chemical analysis. We're then going to look at quite a large topic, rates of reaction, and then salts, specifically acids and alkalis with neutralization, precipitation, and then oxides and hydroxides, and finally a small amount on ammonia. Now, as this is the additional science paper, we won't be going into a huge amount of detail here, but if you've done triple science, you might want to be referring to Dr. Fairless's chemistry 3 parts. Finally, we'll look at electrolysis and try and summarize all the key parts. So the first topic we're going to look at is chemical analysis. And this comes in 2 parts in our GCSEs. The very first is the classic chromatography, chemical analysis which can be done by hand. Now, essentially in chromatography, we have ourselves the following setup. We have some filter paper or some special chromatography paper, which essentially just absorbs our solvent. And what we do is we have ourselves a given line. This line is not made out of ink. It needs to be something that isn't going to dissolve and run up. So it's normally a pencil line. On that pencil line, we can place something such as a food colouring. And what will happen is the solvent will begin to absorb. And what will happen specifically to our food colouring is it will begin to separate. And if it was a food colouring, it would separate into the dyes that make it up. So we might have a coloured dye here and a coloured dye here. Now, the height that these dyes reach is based upon either the size of the atom or how well the actual substance itself dissolves. And what this will do is give us an idea of different dyes within our master. And so if you were given another unknown dye and it had 2 different colours or 3 different colours such as this, we would know that this dye here on the left has this pink dye and this yellow dye. But this over here, it has the yellow dye and the pink dye, but it's got something new. And so chromatography is a very simple way of separating our particular dyes, which are found within a mixture of an original specific dye, such as a food colouring. Now, that's all well and good, but it's a relatively slow process. And so what we might find that we need to do is instead look at an instrumental method, a way to speed up the ability to separate our substances. And so for instrumental methods, essentially, we're using machines. The reason being is the fact that they are very sensitive. They're also highly accurate, but most importantly, they're really fast, and they can analyse huge quantities of information at a much quicker rate. Now, for the exam, the example that you need to learn is our gas chromatography. It's the same principle as our classic human chromatography. In other words, it's separating out a mixture of compounds, but it works much quicker and is highly accurate. Specifically, you need to know the following. First of all, we have a gas, and the gas is what actually carries our substance through a particular column. Now, depending on the actual substance within, it will move at a different speed. That's important because on our gas chromatography, we have a detector. And this detector will essentially record the time it takes for a substance to hit it. This is known as retention time. So essentially, when we look at gas chromatography, we're given a readout, a graph, and the graph will have different peaks. Each peak will represent a different retention time, and that means it's a different substance. We know specifically that having this information about retention time can then allow us to do one final clever thing with a special piece of apparatus, a mass spectrometer. Because what we can do is, based upon the specific positions of these peaks, we can work out the molecular mass. In other words, a very small compound or a very small particle will tend to have a smaller retention time. It will hit the detector quicker, while something very large takes a little bit longer to get there. And so gas chromatography is a way to separate out our mixtures, and we can do it in a highly sensitive way. We can find out specifically the actual relative molecular masses within our given product. So for chemical analysis, there are two parts. The first part is our classic chromatography, our separating of different substances based upon their size or their ability to dissolve. For gas chromatography, the principle's the same. The gas will carry these substances off at different speeds, which will hit the detector and give us different peaks. And those peaks are linked to the different compounds within. So, with that in mind, let's take a look at two exam questions. I'll read it out for you as I did previously, And it might be something that you want to have a very quick look at yourself to try and answer. To the right-hand side, you'll see that the timer in all of the exam questions will begin to go down. So question 1, icing on cakes is tested to check that safe colours were used when they were made. Paper chromatography is one method of testing which colours are in cake icing. The diagram shows an experiment a student did. Now 2 questions. Suggest why there is a lid on the container. The start line should be drawn in pencil, not in ink. Suggest why. Well, let's look at the first question. In this first part, if there's a lid on the container, essentially what we're going to be stopping is our solvent from evaporating and going out. So it's simply to prevent evaporation. Our second question, the start line should be drawn in pencil, not ink. Well, essentially, we need our solvent to not dissolve the line. And if it was made from ink, it would dissolve. So the 1 mark from this part will come from either 2 answers, either saying the ink will dissolve, or by saying that the pencil or the graphite within the pencil will not dissolve. Now, once again, I must apologise for my hideous writing. Here's question 2. I'll start the timer on this one. The diagram shows the results of the paper chromatography experiment. Safe food colourings on the left, colouring from cake icing on the right. Different points within. Question 1. How many different food colours were used in the colouring from the cake icing? Question 2. Is the cake icing safe to eat? And give a reason. Question 3. Gas chromatography linked to mass spectroscopy is an example of an instrumental method. This method was used on a mixture of solvents. Give 2 advantages of gas chromatography compared with paper chromatography. And then finally, what does gas chromatography do to the mixture of solvents? And what information does mass spectroscopy give? Well, let's have a look over on this side. If this was the exam question that we were faced with, the very first point we need to see is that we have some safe food colours. And the arrows point to all 3 areas which will be going up in a line. So we know these 3 colours, these 3 dots, are safe. Well, on our colouring from the cake icing, we have ourselves 1, 2, 3, 4 dots. So let's have a look at the first question. How many different food colours were used in the colouring from the cake icing? There are 4 different colours. However, is it safe to eat? Well, we know this, this, and this are safe. And we find them here. However, we also find that these 2 are not in the safe group. And so to answer this particular question, we would have to say no. But we're only going to get the mark if we give a reason. So we would say the top 2 colourings are not in the safe list. They're not there. Now, for the second part, gas chromatography linked to mass spectroscopy is an example of an instrumental method, and this method was used on a mixture of solvents. The advantages are like we said earlier. We're either going to be saying that it's quick, or we're going to be saying that it's accurate, or we can say that it's sensitive. One of these points will get us 1 mark, but the page is out of 2, so we need to look at 2 specific parts. Now finally, what information does mass spectroscopy give? Well, essentially, it tells us what compounds, if I can spell, or substances we find. The compounds or substances within, or specifically, you could say the mass, the molecular mass of the compounds. I've just got a very quick question from Zoe, which is a good time to answer it. So Zoe's asked, in an exam, can you just call human chromatography paper chromatography? No issue with that. There are, specifically in the exam, they will list very clearly if it is paper chromatography for you. I suspect if they ask you a question involving the word human, they're probably going to be wanting some kind of comparison between human and gas chromatography, human and a machine. So I think it's fine to just essentially have in your mind 2 types of chromatography, chromatography using paper and gas chromatography. In the additional paper, I think that's absolutely fine, Zoe, to have that information and no more. Okay, that's chemical analysis. A slightly bigger part now is part 2, our rates of reaction. And this is a particular set of questions that come up every single year. And they're very relatively varied in what they're going to ask. Sometimes it's a classic graph question. Other times it would be doing some analysis. And sometimes it's a 6 marker. Well, essentially, if we're looking at rate of reaction, a rate of reaction is simply the speed of our reaction, the speed that a chemical process takes place. So that might be something like iron rusting. It goes very, very slowly. It could be something like magnesium burning in air, which goes incredibly quickly. Now, the typical exam questions, regardless of what they're asking for, if they give you a graph, will probably have one that looks like this. Essentially, they're going to have, on one axis, the time it takes for our reaction to happen, and up the side, the amount of product, how much we're making. And then they will have some kind of line. In this case, if this was my original, we've got ourselves a particular reaction taking a certain amount of time. Obviously going quickly to begin with and beginning to slow. Well, if they're looking specifically at that, they might give you some different lines to compare. So for number 2, it's a reaction that's gone quicker. For number 3, it's a reaction that's gone even quicker. For number 4, a reaction that's gone slower. When we look at these particular reactions, we need to think of 2 things here. First of all, the amount of product made. And second of all, the time that it takes. Now, it's not correct to say that a faster reaction will necessarily make more product. It might go off a lot quicker, but end at the same point, in this case, as number 2. So just be careful of that. Just look very closely at what they are telling you. How much product are you making and how much time is going through before that product is made? Well, classic questions for rates of reaction involve 5 things. If you want to speed up the reaction, first of all, you can change the temperature. We'll come on to how in a minute. The second thing that you can change is the concentration. The third is the pressure. The fourth is the surface area. And finally, the fifth is the use of a catalyst. Now, you're going to need to learn all of these 5 different types and potentially talk about every single one. So let's go through them very, very quickly. First of all, temperature. Well, if we increase the temperature of our particles, they're going to be moving quicker. And if they're moving quicker, they're more likely to collide. They're more likely to react. And so particles that are moving quickly because they are high temperature collide more often. And when they do collide, they're more likely to overcome the activation energy needed. We'll talk about that specifically in a minute. So an increase in temperature increases our rate of reaction. The second one that we can look at is the concentration. Now, for concentration, we sometimes combine this with the pressure. In other words, where these particles can go to, or how many there are in a given area. Well, again, the graphs are the same. Essentially, if we increase our concentration, or we increase our pressure, we're going to make more product. Or specifically, we're going to make that product more quickly. If you look in this graph, this demonstrates it well. We've got ourselves 3 different concentrations of actual reactant. They all get to the same end point. In other words, we all get the same amount of mass at the end of it. We just speed them up more quickly depending on concentration or pressure. The third is the surface area. If we're looking at powdered chalk, or we're looking at big blocks of chalk. Well, essentially, if you can take something and make it into smaller parts, you've got more areas for our reactive products, our reactants, to hit one another with. In other words, there's a greater surface area. And that greater surface area means there's more parts that can have activation sites which collide. And the collisions are what cause the reaction to occur. Finally, we can add a catalyst. Now, a catalyst will speed up our reaction, but it won't get used. It has some implicit problems. Sometimes these are very expensive. And other times, when they have actually helped our reaction, they're actually quite difficult to get back. They haven't changed, they're still there, but we might need to find a way to actually remove them from the overall product. That being said, temperature, concentration, pressure, surface area and catalysts all speed up our reactions. Specifically, why? Well, this is all to do with collision theory. Activation energy, less so for additional science, but I will touch on it very, very quickly. Essentially, there are 3 drawings to the left. The first are our different particles. I know there's actually a different number of particles in here, but the idea is on the left-hand side, these particles are moving slowly. The ones on the right quickly. In other words, temperature is at play here. In the middle, we've got our surface areas. And you'll notice on the right-hand side, we've got a lot more parts which can collide with one another. Finally, we've got our concentration or pressure. And so the concentration is either more particles within the system, or the pressure might mean that actually the space that they've got to occupy becomes smaller. Well, with all of this, we need to specifically look at collision theory. If we have more collisions, we get more reactions. And so having some way to increase collisions, be that moving the particles faster, or giving them less space, or having more areas for them to collide with, will increase our rate of reaction. Now, finally, with all of that comes the activation energy. Well, that's simply the amount of energy, the minimal amount of energy that we need for these particles to react. And so sometimes, if we add certain products, such as catalysts, they will lower the activation energy. They will lower the minimal amount of energy you need for the reaction to take place. And that makes it, as long as the catalyst isn't too expensive, a cheaper thing to do. Because we should find that the reaction will go quicker. And so we will make the same amount of product, but in a much quicker time. Finally, with all of the rates of reaction collision theory parts, you're going to need to know two graphs for your exam. These are the graphs that relate to whether our reaction is exothermic or endothermic. Now with this, we're either having heat going out to the system, or we're taking heat in. Well, the graph will hopefully make this relatively clear. If we have an energy quantity versus our reaction progress graph, we'll see the following. In this first example, we have our reactants. These reactants have a certain amount of energy. But when they've done their reaction, we then find that the products are below. They are containing less energy than when they started. In other words, our delta H has changed. We've given out heat. Heat in the form of energy has escaped to the outside world. And so if it's given out heat, this would be endothermic. Sorry, would be exothermic. The contrary to that would be an endothermic reaction. And so for endothermic, something like an ice pack that you would wear if you've hurt your knee. In this example, we would find that energy will need to go into the system. So our reactants would have a certain amount of energy, and by time the reaction had taken place, the products would be higher. The energy has come from the outside system to get it to that point. So exothermic, energy is transferred to the surroundings, normally in the form of heat, whilst endothermic is taking in heat. Now, very loosely, just to keep everything in tide for rates of reaction, you might be asked very quickly in additional science about a reversible reaction. And just remember, that's a reaction but can go in both directions. What you'll find in that particular reversible reaction is one way will be endothermic. In other words, it will take in heat, whilst one way will be exothermic. So that's rates of reaction, collision theory, and activation energy. So let's specifically look at some questions relating to this. A student investigated the rate of reaction between marble and hydrochloric acid. And the student uses an excess of marble. The reaction can be represented by the equation, and here's the apparatus that they used. The student measured the mass of a flask and the contents for 10 minutes. And the results are shown in the graph. Use the graph to answer the question. So here in our graph, we have the mass of flask and the contents in grams, and we have our time in minutes. Question 1. Complete the graph by drawing a line of best fit. Well, hopefully when you look at this graph, and obviously in your exam, it will be in a lot better detail than this, you should see that we seem to have a strange result here. We seem to have an anomaly. So all you need to do for your mark is just ensure that you miss that. So essentially, we'll have a curved line. Ooh, as you can tell, I'm not brilliant on the pen yet. Curved line. We'll do that one more time. Which looks a little bit like that. Hopefully you'll be a little bit neater in your exam. But essentially, you're missing that, what would appear to be an anomalous result. Secondly, use the graph to find the mass of the flask and contents after 1.8 minutes. Well, we've got our time in minutes here. 1.8 is around about here. So we're looking at a number around about 100.3, something like that. Now, I think in this exam, you probably would have been given a slight benefit of the doubt. They probably would have given you the mark somewhere between 100.2 probably, and maybe up to 100.6. You would have been awarded a mark for somewhere around there, depending on how well your line was. Okay, the second part of the question. Now, for this one, I've had to actually take the question formula from the previous, which relates to the question here. So we'll look at that in a second. So the first part, the rate of reaction can be measured by the steepness of the graph line. Describe as fully as you can how the rate of reaction changes with time in this experiment. Well, to do that, I'll just have to go back very quickly to our graph. And again, hopefully in your exam paper, this will all be on the same page to make it nice and simple. Essentially, we're looking at the following. We're looking at what appears to be a quick first part of our reaction, and then a second part where it begins to slow, it begins to tail off. So for this particular question, what can we say about the rate of reaction? Well, for 2 marks, the first mark would be that it starts off quickly, and the second mark would be it begins to slow or even appears to stop. Again, it would never hurt at this point in your exam with this amount of space to add some numbers. For example, after X minutes, we've got Y quantity. Now the second part, the mass of a flask and contents decreased during the experiment. Use the equation for this reaction to help you to explain why. Well, over here is our equation. Hopefully, by looking at it, you can see that over here, on the product side, we're making some calcium chloride, some water, but specifically some carbon dioxide, which is a gas. And so, if we say that carbon dioxide is produced, which is a gas which will escape, we're going to find that very difficult to recall the mass of. And so we should find, because we've produced the gas, that our mass decreases. The carbon dioxide is very difficult to weigh. Finally, the student repeats the experiment using powdered marble. The rate of reaction between the marble and hydrochloric acid particles was much faster. 2 marks. Well, hopefully you're thinking of surface area. The surface area has increased if we use powder. And if we've got an increased surface area, we should find that we have an increased number of collisions. In other words, in the same amount of time, we're going to get the product forming. We're going to get the product forming much more quickly than the original experiment. So that's the rate of reaction questions. Finally, before we get on to the electrolysis part, we're now going to look at salts. Now, this encompasses quite a few different parts of the course. We're going to start off really simply. We're going to start off by looking at acids and alkalis, and we're going to start looking at our different indicators and how we can look at particular different parts. Although I'm very sorry, I'm just going to very quickly come back to a previous question that's been raised about knowing or needing to know the specific names of catalysts. Not really. You might want to have in the back of your mind things like platinum, which are used in catalytic converters that help speed up the reaction. But I think it very unlikely for you in additional science to ever have to name a particular catalyst. It does go into the biology parts, obviously with enzymes, where you will need to name specific enzymes. But in chemistry, I don't think you'll need to be able to actually reel off specific catalysts one after the other. I haven't seen those kind of questions come up as we go through. So, looking at salts specifically, if we have a very quick look, we've got something where we start from year 7. So this is the pH scale, looking at whether or not something is an acid or an alkali. We need to go into a little bit more detail, obviously, than just being able to reel off the numbers. But essentially, the left-hand side are our acids, pH 7 neutral, and above 7, we get into our alkalis. Now, if you're looking at acids and alkalis, you're going to need to have some kind of indicator. The classic one is universal indicator. Again, you won't really need to specifically name lots of different indicators. Just know that an indicator should do exactly that. It should indicate something. It should change based on some particular formation. For example, universal indicator will tell us both acids and alkalis. Now, with this particular part, there are a few key things that you will need to remember. First of all, we need to know why are acids acids and why are alkalis alkalis. Well, an acid is simply a substance of pH 7 or less, and acids specifically will form hydrogen ions when in water. That is what makes an acid an acid. Now, an alkali is slightly different. We don't actually use the term all the time. You often come across this term, a base. Well, a base is actually a substance that is pH 7 or greater. The only time we use the word alkali is an alkali is a base, but it can dissolve in water. And when it does so, it releases hydroxide ions. So two parts here, an acid, hydrogen ions, an alkali, which is a base that dissolves, hydroxide ions. Now, finally, before we go into a huge amount of detail, just remember the following equation. And again, what will actually be asked in the exam will vary, but an acid and base will form salt plus water. Of course, the salt that is formed will completely depend on the acid and the base that is used. And so we'll look at some equations in a minute or two, but that's our first key one to remember. Acid and base go to salt plus water. Now, following that theme, we do have at the top here some examples of some equations, but you'll notice they're very slightly different. Because up here, not only have we got acid and base producing a salt plus water, you also need to know that acid plus metal will form a salt plus hydrogen. So it's important that you remember those. It's very unlikely that they get in an exam question you to answer a fill in the blank such as this. But what they're likely to do is give you some acid or some alkali and ask you what it makes. Well, just remember, you're not going to make something out of nothing. So whatever your reactants are, your product will contain them. So keeping it simple, I'm not going to balance them here. If I had something like hydrochloric acid and I added magnesium to it, I know that an acid and a metal makes a salt plus hydrogen. I need to have products that have hydrogen, products that have chlorine, and products that have magnesium in. And so when we go to that, we're going to make ourselves some magnesium chloride and some hydrogen. If you change the metal you're using, the metal in the salt will change. And if you're changing the acid that you're using, perhaps you're not using hydrochloric acid, perhaps you're using something like sulfuric acid or nitric acid, these will vary. So please be aware of basic balancing of equations, specifically as an absolute minimum, whatever you start with will end up somewhere as a product. It just might have reformed as a new compound. So that's acids and alkalis. Now, there are two further points that you need to remember. Acid and alkali goes to salt plus water. Acid and metal goes to salt plus hydrogen. You also need to know oxides and hydroxides. Well, for oxides and hydroxides, we have our metal we have our acid plus our metal oxide, or our metal hydroxide, and these will form salt plus water. When we look at those specifically, again, some examples here. If we take hydrochloric acid, we add it to a particular oxide, in this case, copper oxide. The salt we are forming comes from the oxide, the metal part within, and the chloride, the chloric acid, to form copper chloride, leaving us some hydrogen and some oxygen, i.e. some water. So there's no point learning these specific ones because they might ask you a varied range in the actual exam. Just remember the rules, please. An acid and alkali goes to salt plus water. An acid and our metal goes to salt plus hydrogen. And finally, our acid and metal oxide or metal hydroxide will go to salt and water. Now, finally, with that point, you do need to know very quickly about ammonia. It's in a lot more detail with the Haber process for triple scientists. Specifically in additional, you just need to know that if you take ammonia and if you then react that with nitric acid, we will make ammonium nitrate. Ammonium nitrate is brilliant because it is a fertilizer. It's going to make our trees grow nice and tall. And so when they get this ammonium nitrate, they're able to take that nitrogen, make lots of amino acids, lots of proteins, and grow nice and tall. Okay, let's take a look at some questions for salts. Again, it might be something that you want to pause and have a look at yourself, because I'm going to go relatively quickly, just a few minutes to read the question for you to see. So, question 1. Wastewater from some industrial processes contains metal ions, such as chromium ions. These metal ions must be removed from the water before the water is returned to a river. A method of removing chromium ions from water is represented by this equation. So the first part will be to balance this. The second part suggests a suitable chemical that could be added to the water to provide the hydroxide ions. And finally, explain how chromium ions are removed from the water. Well, let's look at the first part. If we're balancing this equation, we're going to need to make sure that whatever's on the left is on the right. I'm looking for my quantity of oxygen and hydrogen. And I'll find that on my product side, I've got a little 3 going back to my bracket. In other words, there are 3 oxygen and 3 hydrogen atoms. So to balance, it's nice and simple. The answer will be 3. 3 oxygen on the left, 3 hydrogen on the left, and 3 on the right. For part 2, we need to suggest a suitable chemical that could be added to the water to provide these hydroxide ions. Well, lots of different answers here potentially. The important point is really, we're looking for an alkali. You could say sodium hydroxide, you could say potassium hydroxide, you could say lots of different hydroxides. Some kind of alkali, some kind of hydroxide gets you the mark. Now finally, explain how the chromium ions are removed from the water. The clue is here. We know that this is a solid. And in fact, the state symbols, we have solid, we've got ourselves our liquid, we've got ourselves our gas, and finally, we've got aqueous, which is something dissolved in water. Well, if we have a look specifically here, how are we going to actually remove this? Well, the chromium ions, when added, form ourselves a precipitate. In other words, they form a solid. And so all we need to do to filter out our precipitate is to use filtration. In other words, we need to try and catch the particles through some filter paper. So the clue to this question is quite subtle, but it's in the equation. Now, this is how they tend to ask salt questions. It's a 6-marker. In the real exam, you'd have a lot more space here. I've taken it out just to fit it on the screen. The salt called potassium chloride is made when potassium hydroxide solution reacts with hydrochloric acid. Describe a method for making crystals of potassium chloride from potassium hydroxide solution and hydrochloric acid. In this method, you should describe how you will add the correct amount of hydrochloric acid to neutralize the potassium hydroxide solution, and describe how you're going to get the crystals. In the real exam, this would be a spelling, punctuation, and grammar part. So that's normally separated in bands of 1 to 2, 3 to 4, or 5 to 6 marks. You're going to get a couple of marks for good spelling, punctuation, and grammar. So you're looking for at least 4 good points in this question. Well, let's have a look. Essentially, any kind of answer involving a titration gets you the mark. Specifically, the parts that we would need. Well, the first part, you'd need your reagent. To that reagent, you need an indicator. You then add your other, the other reagent that you're doing to essentially have our neutralization. When you're adding that, you'll be swirling it round and finding out when the indicator changes. You're going to note roughly how long that took. So when you then come to do it again, you'd repeat it without the universal indicator. With that specifically in mind, knowing, I say how long it took, how much we had to use before the colour changed in our indicator, you'd repeat it until you got very close to the quantity used before. And then you'd slow it down until you get a specific quantity used. At this point, we can then take our product and put it into an evaporating basin. Give it some heat with a Bunsen burner or equivalent, or let it dry out in the sun. And this will eventually crystallize, and we will be left with our potassium chloride crystals. So the 4 marks basically come from 2 or 3 marks for explaining a basic titration or adding our acid plus our alkali. Using universal indicator to know the quantities needed before they neutralize, and then repeating without it, because what we don't want to do is burn that. And then finally, when we've got all of it, allowing it to crystallize by heating with a Bunsen or letting out by the sun. Okay, question 6. Relatively quickly this one, because we're getting a little bit tight on time. You might want to pause this and answer it yourself and come back to it. Ammonium nitrate is another salt. Ammonium nitrate is made when ammonia solution is neutralised with an acid. Name the acid to complete the word equation. Well, it's nitric acid with ammonia to make ammonium nitrate. Read the information about ammonium nitrate, good or bad. Farmers put it on their farmland. People are worried. Rainwater can wash the farmland and the nitrate can go into rivers and lakes. And it might get into drinking water. It could be harmful. So there's lots of good points in this small piece of text. Why do some farmers put ammonium nitrate on their farmland? Well, as we said before, it's a fertilizer. Plants will grow. And this final point here, these are questions that often come up. Which one of the questions in the table cannot be answered by science alone? How much ammonium nitrate is in drinking water? Well, we could get a number, so we could find that out. Is ammonium nitrate soluble in rainwater? Well, we can find that out. Yes. Should farmers stop using ammonium nitrate on their farmland? That's the answer. It's a question that is, for our 3 marks, an opinion. Your opinion might differ to mine. Or it includes ethical issues. I think you should use fertilizer, or no, you shouldn't. Or any particular answer that is saying this is a difficult one to talk about. Now, I just got a very quick question from Joe. He's saying, could I say that it dries out and that's how we get our crystals? Absolutely right, Joe. On our previous question where we were looking at essentially doing our titration, by saying that it's going to dry out and form crystals is absolutely fine. That will get you a mark for that part. Okay, ladies and gentlemen, I'm now going to go on to the final part, which is electrolysis. Again, a question that comes up very often in the additional exams. It's relatively straightforward, but you need to know some of the key terms within. We're not going to need to know, for additional science, anodes and cathodes. We're not going to need to know on that part, our particulars in what is being made, but you will need to know specifically that we have certain electrodes, the charges therein, and specifically what's going on. So let's look at part 1, the process of electrolysis. Well, electrolysis is very simple. It's splitting with electricity. So using electricity to split something. Straight away, if we're talking about electricity, there are cost implications. This is not a cheap thing to do. So we need to look at that specifically of why would we do it and the parts that are going on as we go through. So let's start at the very first. Here we've got ourselves some lead bromide. Now, the principles for electrolysis are the same. What we're finding is that we have electrons that are in our ionic substance, and the electricity is allowing the electrons to move. The ions are able to conduct. So putting an electric current through our ionic substance breaks it down into elements. The reason being is that the free ions are allowed to move, they're allowed to conduct. And so we need this flow of electrons, and they're going to be moving, and the movements are very specific that you need to know in the exams. Basically, we have a particular movement of electrons which are flowing through the system. The electrons are taken away from the ions at the positive electrode, and they're given to the other ions at the negative electrode. And as long as they do that, we can atomize our particular reactants. As we go through all of this, there's one key term we need to remember, and it's oil rig. Oxidation is loss, reduction is gain. In other words, electrons are lost, electrons are gained. So let's take a look at this first example. For lead bromide here at my positive electrode, we're going to find that we get negative ions which are attracted to our positive electrode. Opposite charges attract. And so we are going to get ourselves the losing of electrons, and so we have an oxidation. Because of that, we find that we produce bromine. We have ourselves the negative ions moving across. On the negative electrode, we have the positive ions, which are attracted to this negative electrode. In other words, we're having a gain, reduction. Reduction is our gain of electrons. And so what we find here is we actually then produce our lead. The lead moves across. So in our electrolysis, we've got two parts going on. We're forming our lead. We're forming that because the negative lead ions accept the electrons. And in doing so, they become a lead atom. On the other side, the positive electrode, we get our two bromine ions. And they're both losing an electron. And by doing so, they become bromine. So this is electrolysis of lead bromide. Now there's two more types of electrolysis that you need to see, and hopefully by seeing a couple, you'll start to understand what's going on. Again, we've got a positive electrode and we've got a negative electrode, and we've got the flow of electrons. In this particular case, we're looking at sodium chloride. But again, the principles are exactly the same. We're going to have our negative ions, which are going to be attracted. Oxidation is lost. So we are going to find that chlorine is produced. Whilst on the negative electrode, we're going to find that we have the positive ions attracted. Reduction is gain. We're going to have hydrogen produced. The hydrogen ions will gain the electrons. But chlorine, they were losing their electrons. So our chlorine ions are losing the electrons, becoming chlorine molecule. What we also get is this, sodium chloride. Now, the reason we get this is because the sodium ions stay in the solution, because they're more reactive than the hydrogen. The hydroxide ions will also form water. So from that, the hydroxide ions within will leave us an NH NaOH solution. So in this example, we're actually getting 3 different things produced. We're getting some hydrogen. We're going to get ourselves some chlorine. And finally, the hydroxide ions from the water, along with the sodium, will leave us with sodium hydroxide. 3 very important things for manufacturing of soap and other products. Finally, if you're doing triple science, and maybe if you're unlucky in a higher paper, you will need to very quickly know the half equations. 2 parts of this. Just ensure that the number of electrons are the same for both half equations. In other words, 2 electrons, 2 electrons. So if we look, I've got myself at a negative electrode, my hydrogen ions gaining 2 electrons to form hydrogen. At the negative, I've got myself my chlorine ions, which will break to give me a chlorine molecule and release my 2 electrons. Now, in terms of exam questions, they like to go for one specific part normally. It will either be describing the electrolysis of sodium chloride or lead bromide, or it might be this particular one, which is how we produce aluminium. Aluminium is very widely abundant, found in lots and lots of ores around the world, but it's stuck to different things. Specifically, it's always stuck to oxygen, which doesn't make it very useful. And so, just as before, aluminium can be electrolyzed to form a pure metal. But as we go through that, there are a couple of things that you need to be aware of. First of all, we use a product called cryolite. Now, cryolite massively reduces the temperature which is required for the aluminium oxide to dissolve. It must be dissolved to allow electrons to move. But it reduces the temperature hugely, by about 1,000 degrees. So that makes it significantly cheaper to do. Second of all, the specific electrodes are made out of carbon. And one of the products that we're going to get from the electrolysis of aluminium oxide is oxygen. Well, that will react with the electrodes to form carbon dioxide. So they do begin to wear away. Finally, with electrolysis, along with our soap from the electrolysis of sodium chloride, we find that we can use it for electroplating. Electroplating is basically taking a cheap metal and allowing electrolysis with a more expensive metal to go around the outside of it. In other words, you can have a cheap brass cup, but you can electroplate it with a tiny piece of silver. So it looks silver, it looks really expensive, but actually it's relatively cheap because the amount of silver you're using is very small. Specifically for that, with electroplating, you just need to know that the object that you are going to specifically plate up needs to be on the negative electrode. That's where the object needs to be, because we'll find the ions will move over to it, and in this particular case, our silver ions will move across. Okay, we're going to end on the following question that is typical of an electrolysis question in the exam. 2 parts to this. I'm just going to show you this one firstly. It's a 6 marker, although we've already had a 6 marker, and in your exam you'll only ever be given 1. but there are two parts to this one. I will show you it because this is often how they do ask for electrolysis. With this one specifically though, this is the information that they gave at the beginning. So aluminium is made from electrolysis of aluminium oxide. It's an ionic compound. It's got our aluminium ions and it's got our oxide ions. And then here's the apparatus that is used. So we've got our negative electrode, our positive electrode, and then we've got our molten aluminium oxide dissolved in cryolite, and we're releasing carbon dioxide. So for the question, explain as fully as you can how aluminium and carbon dioxide are formed in this process. Well, the first mark is from you saying, essentially, we need to melt our aluminium oxide. We're then going to say that our aluminium ions are going to be going to the negative electrode. We're then going to have the following. We are going to form aluminium atoms at the negative electrode. Two other parts to this. We're going to find that the oxide ions are going to be attracted to our positive electrode, and that's going to form oxygen. Now here's the key part. If we're forming oxygen on our positive electrode, which is made from carbon, we're actually going to be making carbon dioxide. So aluminium ions moving to the negative electrode, forming our aluminium. The oxide ions moving to the positive to form oxygen, which combines with the electrode to form carbon dioxide. For part two, aluminium is a metal. Explain why aluminium conducts electricity. Well, this goes back to metallic bonding. We've got a sea of delocalized electrons. These electrons can move, and if they can move, they can carry charge. Here's our final question. Aluminium extracted from the aluminium oxide using electrolysis, and the diagram shows it. It moves on. This was in the previous question that I've just put into this part for us to see. The electrolyte contains cryolite. Explain why. Well, if you remember, it's going to reduce our melting point. You won't get a mark for saying boiling. We're not boiling the aluminium oxide, but we are melting it. And if it reduces the melting point, it is cheaper. Or you could say it's less likely to melt the actual bits of equipment that you're using. For a balanced equation, well, we're going to have ourselves here our oxygen. How many electrons are we going to be making? Well, we're actually going to find ourselves with our 2 oxygen molecules here. And if we've got 2 times 2 for our ions, that must leave us with 4 electrons. Finally, using this particular diagram, the positive electrode in the cell is used up during the process. Explain why. Again, if you looked at the previous question, the diagram had carbon dioxide forming. It's because our electrodes are made of carbon. The carbon will react with the oxygen during the electrolysis, and together that will form carbon dioxide. Ladies and gentlemen, I hope that was relatively useful for you tonight. Again, all of these PowerPoints and interactive YouTube clips are saved online. Don't forget, this forms a wide part of your revision with the revision cards, using online videos. Revision Monkey is a website with many on there. Brainscape cards, your CGP books, lots of past papers, and then speaking with friends, testing one another. Don't forget, all the resources are on the website. I'll stay on the chat forum for a few more minutes if anyone's got any more specific questions. But I hope it was useful. The very best of luck with your exams. We will continue with 2 physics additional hangouts, and we'll hopefully have those up and running by the weekend. We'll also do 2 biology and triple scientists. There will be a physics and a biology coming. I hope you enjoyed it and have a very nice evening. Good night.